Okay, so let's begin. I'm sorry for being late. I'm not feeling very well today, so I may go very slowly. I hope everybody doesn't mind. If I occasionally forget 1 + 1 = 2, let me know. Okay. So let's first finish the regularization lecture today, and I'll begin something new. But before that, let me. Okay. Remember what we said last time about regularization. Right? So regularization has this very general term where we're minimizing the in-sample error. Okay, something like a L2 loss function plus lambda times something that's called a penalty, which is a measure of model complexity. So this penalty term in lasso and ridge regression is basically beta 2 norm or beta 1 norm, right? So it's the simply these two is what we have seen as a measure of complexity, and they make sense because the larger the beta, right? The more complicated model gets, it gets more flexible. So so these are model penalties, but it turns out that we not only it turns out that we have any kind of penalty. It doesn't have to be these two. We can have many custom designed. So one of the things I said last time is, suppose we have something like this. The penalty is j times beta j squared. Then it has the effect of particularly penalizing the coefficients with large j, which is the letter terms. So this would, for example, if you have a polynomial model and you don't want you want the model to be simpler in the sense that you don't want the higher order polynomials, then you can use this type of penalty to penalize the higher order more, right? So this is the one thing that we talk about. But really, you can have anything, right? So you can not have anything, but you can design a lot of different kind of penalties. So in general, for example, even if we're just talking about penalty on beta, you can do one norm, you can do two norm, right? But in general, we can do any norm, okay? We can do, let's just say Q norm, right? Can we do that? Just Q norm. The ideal is I can essentially penalize the sum of j, beta j to the qth power, okay? So that would be a qth norm. So the q can be 1. In this case, we have which one? Do we have a ridge or lasso in this case? If it's equal to 1, is a lasso or ridge? It's a lasso, right? If it's a 2, it's a ridge. But it can be a lot of things. Right? It can be 3, 4, even 0.5, right? So if we plot different kind of things, we say the q equal to 4, q equal to 2, they look like this. Q equal to 1 is our lasso. Q equal to 0.5 has this shape. 0.1 increasingly shrink, right? Okay, just judging from the shape, which of these q values have the effect of doing variable selection? Because ridge regression do not do variable selection, right? But lasso does. And we sort of gave intuition last time. Why? And the intuition is this page, okay? It's long back. Right. What is that? Yeah, okay, so people see that this page, this is the intuition. We're minimizing our objective function subject to a constraint. And the lasso constraint look like this one, the ridge regression look like this one. That's why we get a lot of corner solutions with a lot of beta equal to 0 for the lasso. Okay, so for different q, which one do you think have the variable selection effect? Meaning, which q will shrink coefficients to exactly 0 as the ability? Can we do this? So it turns out, I hope this is obvious to you, but it turns out that this one can, not this one, right? Okay, because see that it's convex, and there's no way for you. It's very hard to get a corner solution here. Okay, So that's why we have the lasso. We have, if q equal to 0.5, we can do the same thing with the lasso. It also has the effect of achieving variable selection, of shrinking variables to 0. What is q equal to 0? What if we have q equal to 0? Well, q equal to 0 is actually not exactly defined. Okay, so it's so the norm, when we have 0 norm, what does beta 0 norm mean? Well, it turns out that if the beta q, right, q norm, but q, the limit of q goes to 0, okay, it doesn't have the example, we can go to limit, is actually equal to the sum of I beta not equal to 0. Okay? So it's like this. It's the sum of beta, if you will. Okay? The sum of existing beta. Well, let me actually I should say this. Just the sum, right? Just the so if beta is beta itself is a p times 1 is a p times 1 vector, then this equal to 0 will just be p. So just how many beta there we have. Okay, how many beta we have. So what if we use 0 norm? What if we like q go to 0? We use 0 norm. What kind of penalty is that? What does it penalize? So the 2 norm penalizes beta square, sum of beta square, right? It's the 2 norm. The 1 norm penalizes the sum of beta absolute value. The 0 norm penalizes what? Penalize how many beta we have, right? Just if beta is p dimensional, we just have p. Okay, so penalize how many beta we have. Have we seen that method? Have we seen any method that penalizes the number of beta? Just number of beta. We don't care how large it is. Just as long as you are there, we count you, and we penalize you. Have you seen that? The answer is yes. We have already seen it. Something that's basic regularization using the 0 norm. Let's go all the way back. Do people remember what AIC BIC does? For AIC, this negative log likelihood, you can think about basically in-sample error, right? So AIC is in-sample error plus 2p. So 2p is, p is the dimensional beta. Okay? So what AIC doing is penalize the dimension beta, which is 0 norm. So you can think about AIC and the BIC, this information criteria. Essentially, if you use the information criteria to choose your model, you are using the 0 norm to regularize your model. It's really that simple. Okay. So it says the more beta you have, the worse, right? Conditional on the same mean sample fit. Okay, the same mean sample fit, the more beta you have, the worse, which is exactly the 0 norm of beta, right? And we have already do it, which is the AIC BIC, that is 0 norm. Okay. So there's a natural connection between all these methods. Whether if you're using AIC BIC to do forward stepwise regression, you're essentially doing the 0 norm regularization of your model. And if you do ridge regression, it's a 2 norm. If you do lasso, it's the 1 norm. But they're all penaltying on beta. Okay. Now, it turns out that the penalty doesn't have to be on beta, on the coefficients. It can also be on other things. So, for example, I can require the penalty to be, if I have a model like this, right, something like that, I can have my penalty to be not exactly on the linear beta coefficient, but I can have it on the derivative of my function. So if I want my function to be not varying too much, okay, I want it to be linear, for example, as linear as possible, then I can penalize on either the first derivative. If I penalize the first derivative, I want the first derivative to be close to 0. If the first derivative equals 0, it's something like this, right? Also, I can penalize the second derivative. If second derivative, also I want to make this as smooth as possible, right? Right? If it's very jumpy, it's not smooth. If it's discontinuous like this, then it's not good. So I want it to be continuous and smooth. I can penalize the second derivative. So you can do penalty on anything. Now, if I penalize so if I do this, right, I minimize y minus a function, and this function can be any function, okay? But then it can be all the function forms you can ever imagine. We don't put any constraint on a function form, but I penalize the second degree derivative, second order derivative of the function. If I do that, that gives me exactly this what's called a smoothing spline, okay, which can be a very smooth thing. Now we have already talked about regression spline. The idea of regression spline is we divide the X region into several regions. We fit a, say, third degree polynomial in each region. That's called a cubic spline. The smoothing spline turned out, I won't go through the math, it's in my slides, you can go over it, but the smoothing spline turns out that if I minimize this in-sample error, but I allow any function, okay, any type of function, I don't put any restriction on function, but I just regularize on the second order derivative, I get a cubic spline. The result will be a cubic spline, but the cubic spline has a knot. Remember what a knot is. A knot like a cut point, okay? So in the regression spline, I cut it, divide it in two regions, that's one cut. A cubic spline that makes a cut at every data point is a smoothing spline, okay, something like that. So if we it can be mathematically proved, if we minimize any functional form, okay, choose any function form that minimize the second order derivative, we get a cubic spline with a cut at every data point. Okay, and also shrink towards zero. Okay, that's what I say, and you get something very, very smooth. That is. There's another example of regularization, right? But I won't spend a lot of time to talk about it. If you remember from our regression lecture, right? When we talk about cubic spline, what do we say? We say, look. If I divide my region into like two space, okay, just one cut, so this is one cut. I want to fit a third degree polynomial here, and I want to fit third degree polynomial here. But we make several constraints. The constraint is, first of all, they have to meet at the same place. This is called continuous, right? They have to be continuous. And the second is the first degree, the first order derivative has to be the same. And the second order derivative has to also be the same. So by doing that, we make this curve smooth and continuous around this border, right? So this is a constraint. But what is a constraint? A constraint is a regularizer. It regularizes the shape of the curve to make it more smooth. Essentially, that's what it is. Okay, it constrains the curve from becoming too wildly, discontinuous or not smooth. So regularization is a very general idea. It's basically putting a constraint on our fit. Okay, that's all it does, right? So anything that does this, you can think about as a regularization method. Okay? All right. Now, anyway, so let's talk about another kind of regularizer, right? So regularizer can be anything. It can be the betas. It can be the second order, first order derivative of the function. Let's talk about another case, which is this. First of all, when we have a high dimensional data, or when we have, in general, when our x variables are highly correlated with each other, then there's a problem, right? So the the multicollinearity is a big problem, especially for the lasso. Let me explain why it's a particular problem for the lasso. It turns out that lasso shrink variables to zero. But if there are two x variables, x1 and x2, they're highly correlated. Which one does, in a sense, they're very similar. Which one does the lasso shrink to zero? Does it shrink to 0x1? Does it shrink to 0x2? It turns out it's very random. So lasso does very random. There's no clear rule, and often it's very stable results. Let's imagine these two cases. Let's imagine a case, okay? Suppose my true function, this is my true function, y is equal to fx equal to 4x1, okay? There's no x2. Now, what I'm going to do is my model is w1x1, w2x2. So w2 should be equal to 0 because there's no x2 here, right? However, now I'm going to make x1 equal to x2. What does it mean? So I have x1. I just make a replica, okay? Just another x1, but I'm calling it x2. So the correlation between x1 and x2 is exactly 1. Okay, they're the same thing. All right. If I fit this model, if I have x1, x2, and they're exactly the same, and I use this model to fit the y, what kind of W and W2 do I get? Right. Well, let's think about it. So first of all, what kind of W1, W2 do I get if I do OLS, or if I do L2 loss function? Well, L2 norm, sorry, L2 norm under W. First of all, if I, because the true model is 4x1, any combination of W and W2, as long as their sum is 4, will satisfy exactly the true model, right? So we can have W1 equal to 3, W2 equal to 1, or this 4, this is 0, this 0 is 4. It should all give you the perfect true model. So all of these combinations, 4, 0, 2, 2, 1, 3, even minus 1, 5, they all satisfy. Okay, all satisfy the same condition. Okay, so which one would the lasso pick, and which one would the ridge pick? That's the question. All right. Now for lasso, it will calculate the one norm. The one norm is if W1 is 4, W2 is 0, the one norm is 4. If they are 2, 2, the one norm is 4. The 1, 3, the one norm is 4. Because the one norm is always what? The absolute value summed together. Okay? So it's always 4. The only case that's different is minus 1, 5. Now in that case, the minus 1, the absolute value is 1. So that's right. But it's all 4, 4. So lasso doesn't care. For lasso, all three of these cases are equivalent. Okay? They don't represent any difference in the penalty. How about the ridge? For the ridge, 4, 0 give you 16, 2, 2 give you 8, 1, 3 give you 10. So, what does it mean? For ridge regression, the two norm, if we use the two norm as a penalty, which one received the smallest penalty? The 2, 2. The other things have a larger penalty. So ridge regression will clearly prefer which model? The 2, 2 model. Okay. So in other words, for the lasso, it doesn't differentiate between these cases. It will shrink to 0 very randomly. But for ridge will not shrink to exactly 0. It will shrink. But it will shrink so that these two go down together. Because they prefer these two coefficients to be about the same. Because if they're different, they end up with a different two norm. Right? So for ridge regression, they will shrink the very correlated variables. Ridge regression will shrink them together toward 0. But lasso will shrink them very randomly because it doesn't care. All right? Okay. So, question, right? How do we... So I want this. I want the ability of lasso. So I want to benefit lasso. I want to shrink coefficient to 0. I want variable selection. But also, I want to deal with collinearity. I want to deal with this very correlated, this difficulty, right? Because lasso doesn't do them very well. How do I combine the benefit lasso with the benefit of ridge? Because ridge shrink down, very smoothly, uniformly together. Lasso shrink in a very random way, causing the final model very hard to interpret. So how do I do lasso while having some benefit of ridge? That brings us to elastic net. Okay, so that's the name where the elastic net comes from. The elastic net is the idea extremely simple. We just change the penalty so that the penalty is a weighted combination of the lasso and the ridge. Okay, so we just let the penalty equal to alpha 1 norm plus 1 minus alpha 2 norm. That's it. And alpha controls the mix of lasso and the ridge. If alpha is large, alpha is always between 0 and 1, right? But if alpha is close to 1, what do we get? We get very, very lasso, okay? But if alpha is close to 0, we get very, very ridge. And if we plot it, then the elastic net look like this. So it's between the lasso and the ridge. It still has some variable selection effect. But, it's better than lasso in shrinking correlated coefficient towards 0. So here's again simulation. Anytime you're not sure how your method works, do some simulations. Right now our y is equal to 3z1 minus 1.5 z2. So that's a true model. But I generated 6 different x. 3 of the x, so x1, x2, x3 is only a function of z1. And x4, x5, x6 is only a function of z2. Okay, so 3 different x, 3 different x. So in other words, x1 to 3 is correlated. with each other. X4 to 6 is correlated with each other, right? They both matter because the underlying model is Z1, Z2. So what I'm going to do is I'm going to regress 1 on Y on X1 to X6. No Z, okay? Just regress Y on X. X has a 6, we have a 6-dimensional X. Now I'm going to do a lasso, and the lasso, the command in R is Xiamen X, Y, alpha equal to 1. People remember this, I hope. Now here the alpha equal to 1 means we're doing a lasso, right? And remember, alpha equal to 0 means we're doing ridge. Now, I have never explained what does alpha mean. We only talk about lambda. We didn't ever talk about alpha, right? But what is alpha? Very simple. Alpha is the mixing coefficient, okay? Alpha is elastic net. Alpha here is the mixing coefficient. So alpha equal to 1, we're doing the lasso. Alpha equal to 0, we're doing the ridge. If you specify any alpha between them, you are doing elastic net. Okay. That's where it comes from, all right? So now I'm going to do alpha equal to 0.3. That's a 30% L1 and 70% L2 norm. So that's a pretty ridge-like with some lasso effect. All right? Okay. Here's the result, right? If we look at the elastic net and the lasso, remember we have 6 different X. 3 of them are correlated, 3 of them correlated. For the elastic net, it's very smoothly shrink to 0. Very smoothly. Continue together uniformly, I should say, right? So all 3 shrink together towards 0. For lasso, it's completely random. You have no idea, okay? Depending on different places, some X is 0, some X is not 0. Right. Okay, so elasticness provides a way to improve upon correlated features, right? So if features are correlated, you can try elasticnet to avoid this randomness in shrinking. All right. Now, regularization and especially shrinkage methods like the lasso and the ridge are mostly frequentist methods. Okay, so they are developed by frequentist statisticians, and they're not in essence they're not Bayesian, but we can give a Bayesian interpretation to the lasso and the ridge, which will be extremely helpful to think about what regularization actually means. Okay. So like I said, regularization is a constraint on the complexity of the model. Right? We start with a complex model, and then we use a penalty on the complexity to bring the complexity down, to constrain the shape, right, of our function from become too wildly, right, overfitting. Now, the Bayesian way to look at it is this. First of all, what is Bayesian? I think all of you have some sense of Bayesian, and I'm not going to go deeper than the basic sense, right? So Bayesian is very simple. There's a prior, there's a posterior. The prior is what you think about the data, think about the phenomenon before you're seeing this data. Posterior is what you believe, what your belief is after seeing the data. Now suppose we are talking about the prior and the posterior for the theta. The theta is the parameter for a model, right? It's like a beta, right? The beta in the linear models. So I want to know what the beta is. I want to know what the beta for the linear model is. Now, before looking at the data, I have some idea about what the beta should be. After seeing the data, I have a new updated belief about what the beta should be. So that's the prior and that's the posterior, right? Okay. Now, the question, suppose this is my posterior, okay? This is my posterior. Suppose my, I just want one theta value. I don't want a distribution. There's a distribution. It tells me the posterior distribution, like how likely theta is. But I just want to have one theta value, okay? Just tell me what the most likely theta is. Well, you can do the mean, okay? Again, that just, it's decision theory, right? You can do the mean, you can do the median, you can do the mode. Let's do the mode, okay? The mode is the theta that corresponds to the highest probability. In other words, according to my posterior distribution, what is the most likely value of theta? That's the mode, okay? The mode is here. That's the most likely because the probability is the highest. For that, we have a name, which is called the MAP estimate, the maximum a posteriori estimate, okay, MAP. Yeah, it's a posteriori, I don't know how to put it. Anyway, the MAP estimate is the maximum of the posterior distribution where the posterior is defined as p theta conditional on seeing the data, right? After seeing the data d. Right? So if I maximize this probability, the highest probability point, then that's giving me the MAP estimate, which is the mode. Okay, this mode. All right. Now, the MAP estimate is typically different from the MLE. All right, only in the case of uniform prior. So remember how we do MLE. The MLE is to maximize. What does the MLE maximize? MLE maximizes the likelihood, but what is the likelihood composed of? Do people remember? The likelihood is the probability of seeing the data conditional on what? A theta, right? Correct? It's, given the theta, what is the likelihood of seeing the data? And we construct the likelihood based on that. The MAP is what? The MAP is the probability of theta conditional on the data. Okay, so it's like our discussion of p-value again, right? It's very similar. So, what is the relation between them? Well, so what is theta conditional on d? What is that? That is the distribution p theta d pd, right? Okay. Now, but what is this? This is just probability of d given theta, p theta divided by p d. Okay? All right. So if I choose a theta to maximize this thing, I am choosing a theta to maximize this thing, but then I can get rid of the pd. So essentially, if I'm argmax the p theta given d, then equivalently I'm argmax. I'm doing is argmax p d given theta p theta. Correct? Okay. All right. So what are these two things? Well, this is our log this is our likelihood, right? This is the likelihood function, which given theta, what is it probably seeing the data? What is the p theta? P theta is in Bayesian terms our prior belief, okay, prior belief before seeing the data. So the posterior belief is composed of the prior belief plus the likelihood, right? You can think about it that way. So the MLE is maximizing this likelihood. The MLP is maximizing this posterior distribution. They are equal only when what? Only when this prior, this p theta, always equal to 1, right? Always equal to 1. Do we have this kind of prior that probability is always equal to, or maybe not 1, but it's some constant, right? Constant, okay? Do we have a prior where regardless of the value of theta, the probability is always going to be a constant? That's the uniform prior, right? Okay, so theta. So right, if theta value is between, if I know theta is between 0 and 1, then uniform prior is p theta is equal to 1 in this set, right? If I know theta is from -1 to 1 uniformly, then p theta is equal to what? 0.5, right? 0.5 in this region, because it has to integrate to 1. It's always constant, but it has to integrate. What if theta is from negative infinity to positive infinity? Then this p theta, if it's uniform, is almost close to 0, right? It's approaching 0, but it's not 0. So anyway, in that case, if we believe that theta is uniformly distributed from negative infinity to positive infinity, it is called an improper prior. Improper because it does not, for any constant that is not equal to 0, it does not integrate to 1, because it's negative infinity to positive infinity, so it's improper. But people use it anyway. People in Bayesian use it a lot, right? When you do actual analysis, they just assume that p theta could be anything, and we have no knowledge about where it is. That's uniform distribution. Okay. So when p theta is uniform, MLE equal to MIP. Actually, I can make even bolder statement. I can say when p theta is uniform, frequentist equal to Bayesian. Bayesian become frequentist. Why does Bayesian become frequentist? Well, because the MLE equal to the MLP in a sense. The reason why the Bayesian become frequentist when p theta equal to 1 or p theta equal to constant, uniform, theta is uniform is because if we assume theta is uniform in our prior knowledge, what does that say about our prior knowledge? It says in our prior, we know nothing about theta. We just know that it exists everywhere with equal probability. So we essentially we know nothing about theta. So essentially all our posterior knowledge come from what? Come from which one? Come from the D, okay? Come from the data. Okay? So essentially all the posterior distribution, the shape, come from the data. It doesn't come from prior because our prior is uninformative. It doesn't tell us anything. It's uniformly distributed from negative infinity to positive infinity. Who cares, right? It doesn't tell us anything about theta. So all our knowledge about theta come from our data. And that's frequentist. Because for frequentist analysis, every conclusion only comes from your data, existing data. It doesn't come from your previous knowledge, right? Frequentist is an approach that does not incorporate prior knowledge. We have already talked about that when we were discussing p-values and how to interpret p-values and the research design, etc. Right? So frequentist is a method that does not incorporate prior knowledge. So if you're doing Bayesian, but you're assuming sort of a uniform prior over an extremely large range, you are essentially doing frequentist. There's no difference between the two. Okay. All right. So it turns out, okay, lasso and ridge regression is essentially a MAP. If we look at them from a Bayesian perspective, they're an MAP estimate corresponding to a particular prior distribution. So the lasso and the ridge regression can be thought about as Bayesian methods with a particular kind of prior. That's it. Okay. The MLE, right? Because the lasso and the ridge is not MLE. But the MLE, let me just say, okay. So let me define. The MLE is estimate, or the regular, the OLS. Let's say the OLS estimate minimizes the in-sample error. So the OLS can be thought about as something that without any prior. So if our prior distribution is uniform, uninformative, we can think about the result as an OLS or MLE. Same thing, okay? Basically minimize the in-sample error. But lasso and the ridge are essentially the MAP estimate, but with a different prior than uniform. Okay? But what kind of prior is that? Let's first go to the derivation, all right? Okay. So, well, actually, no. Let's go back to. Let me just tell you. Okay, let me just tell the result first, then we go to look at the derivation. But it turns out that the lasso and the ridge are essentially a non-uniform prior. That's the difference between them and the OLS and the MLE of linear models. Okay, for linear models you can do OLS, and if you assume a normal distribution to the error, it's MLE, right? It's MLE. You can do MLE of the normal linear model. Those estimates corresponding to a Bayesian, but with non-informative prior, with the uniform prior, because essentially we're getting all our information from the data. But the lasso and the ridge correspond to Bayesian method with this kind of prior. Okay, this non-uniform prior. For ridge regression, it is this uniform distribution centered around zero. For lasso, it is this Laplace distribution centered around zero. That's essentially the Bayesian way of looking at lasso and the ridge. They're essentially Bayesian MAP estimate with a prior distribution that look like this. Now, why is that? Right? Before looking at the mathematics, because the mathematics is easy, but before looking at mathematics, why is that? Why does this work? Why does this give us ridge? And why does this give us lasso? Well, remember in Bayesian, two things influence our final posterior. One thing is the data, right? The other thing is the prior. So if a prior look like this, and our data tell us that theta is likely to be larger, then our posterior is something like this, where theta is large, but we are still influenced by the prior, right? Okay. So if the prior is uniform, then whatever the data says, that's your posterior. But if the prior is a normal distribution around a zero, then what does that tell you about your posterior distribution? It tells you that the posterior distribution can be influenced by data, but still has to be somewhat close to this normal distribution around zero, right? Okay, because your prior says it's very likely to be around zero. In other words, even if your data tell you the theta is large somewhere here, your posterior distribution will still be closer to 0, like a normal distribution, because that's where your prior is. Two things together determine your posterior. So for the ridge regression, the prior is a normal around 0, and depending on how large the standard deviation is, if the standard deviation is very small, then we are very close to 0. So the prior tell you that beta is very close to 0, very, very close to 0. So even if the data can tell you it's far away, our posterior should still be what? Should still be close to 0. Okay? So in other words, our prior distribution is regularizing my beta, right? People understand? So in the end, your result is closer to 0. Okay? I hope I see some confusion there, but maybe some graph is better than sort of at this point. So after seeing data, okay, so before seeing the data, if my distribution, prior distribution is uniform, meaning it can be anywhere, then after seeing the data, my posterior can be something like this, okay? My posterior can be something like this, which is very far away from theta, okay? Theta equal to 10, for example. But now, if my prior is that theta is very closely correlated to 0, very closely around 0. So that's my prior. Then after seeing the data, the posterior will be much closer. It will be something like this. It will be moved away from this direction all the way toward the prior because the prior also determines, right, because it updates on the prior. So in other words, by having a prior distribution that's around 0, our final estimate will move from here to here toward 0. That's exactly the ridge regression, because ridge regression shrink the beta toward 0. Okay, toward 0. So that's why the ridge regression is essentially a Bayesian method with a prior of beta values centered around 0. That's why its posterior will be shrunk toward the 0 direction. Okay. Okay. Lasso is the same thing. Lasso is just a different shape. Okay. It's just a different shape of prior distribution, the Laplace distribution. Now, if you're not convinced, you can always go to take a look at the. Wait, what's going on? So apparently the appendix is not working in the slide, so let's just manually go to appendix. Here's a manual way of going. Okay, all right. Yeah, so let's consider a simple case, right? We have a linear model, y is equal to linear normal model, because when you do Bayesian, everything is probabilistic. So y is a normal model beta x, but there's a with plus e, but the e is a standard deviation sigma square. Now I assume we already know sigma square. Okay, this we already know, but we do not know beta. So my prior, so without knowing anything about my prior about beta, is a normal distribution, standard deviation tau square. Okay, so my prior is this normal with standard deviation tau. You can think about tau, standard variance tau square. Now, given this information, what is the posterior distribution? Well, like I said, the posterior distribution, maximizing the posterior is basically maximizing prior times the likelihood. So this is the likelihood, okay? It's a normal distribution, y minus beta x. This is the prior, because the prior is just basically this normal distribution beta here. And of course, we can, simplify that. It turns out that you just take the log, do a bunch of math, and in the end, we arrive at this, okay? So what beta is the solution of the RSS, okay, y minus beta square sum plus this lambda beta 2 norm. That's it, okay? So it's exactly equivalent to lasso. Now the only thing is, what is the lambda here? The lambda here corresponds to sigma squared divided by tau squared. So the lambda here is equal to sigma divided by tau squared. Okay, so that's a lambda. Now, what is sigma? Sigma is something we already know. So I'm not doing anything about sigma. Okay, sigma is fixed. It's the variance of y. But this tau, okay, tau is my prior of beta. So this tau is the standard deviation, right? This tau measures the standard deviation of this normal distribution. So what does it say about? So when we say lambda is equal to inverse tau, it's inversely related to tau. What does it mean? It means that the larger the tau, the smaller the lambda. The smaller the tau, the larger the lambda. So what does the smaller tau mean? What does lambda being large means? When lambda is large, we know that means it's a heavier penalty. So we're shrinking more towards 0. So large lambda is associated with a smaller tau. What is smaller tau? Small tau says our prior says they are more closer to 0. So of course that shrinks more to 0. Okay? So that's the equivalence, all right? Okay. So essentially, so why would you ever talk about the Bayesian perspective? Right? Because you already know how to do lasso and bridge. You don't need the Bayesian perspective to do it, but the Bayesian perspective helps, because the Bayesian perspective or the Bayesian interpretation points out that one way to think about regularization is that we are using why we are doing regularization is because we are incorporating our prior knowledge. The frequentist way, which was when we're doing OLS and when we're doing MLE, OLS, the frequentist method, we are not incorporating prior knowledge, like we said, right? So we, just everything comes from the data. But if we have some prior knowledge about the world, then we can introduce into our method by introducing regularization. So because the regularization term corresponds to our prior about what the world looks like. So for example, if your prior is that the model should be sparse, in the sense, we're looking at a huge, in the example I just gave, we have to look at it like election data or some other data we'll look at it in the future. So one of the data sets I was, we'll take a look at, for example, in the future is the supermarket entry data, where we have supermarket, whether they enter into a market, not enter into market. And in each market, we just collect a huge number of variables, like unemployment rate, the crime rate, age of kids, and the age of people under 10 or above 30%. Huge amount of data. We do not know which variable determine whether the company will enter the market or not. So we can do this lasso or ridge, right? But what about our prior knowledge? So our prior knowledge, what do we believe about how companies actually decide whether they enter the market or not? When they actually decide when they enter the market or not, are they really influenced by the 100-dimensional variable? Right? Or do they really consider 100 different variables and see whether we want to enter this market? No, they don't. Okay, so when the analysts perform an analysis of a market potential, whether they want to enter or not, consider the variable is very limited. It's just we don't know. So we choose we pick a huge set of variables and just try to find out which variable matters, right? So in other words, according to our prior, we think the true model should be sparse, in the sense that the true model should have only a few limited important variables. But we don't know them. But if we throw 100 variables in, but our prior says a lot of beta should be equal to 0. Okay? In that case, let's do regularization. Because regularization incorporates this prior, the many beta centered around 0. So this is one way to look at shrinkage method. We also take a look at a smoothing spline, right? Smoothing spline is choosing any function to describe the data, but we regulate on the second order derivative. Also, we took a look at regression splines, where we make the different splines, we make them to be continuous and smooth. So like I said, continuous and smooth itself is a regularization, because we don't know whether the underlying, right? Because ideally you can just let the data do anything. You can just fit any complex function on the data. But why do we need smooth and continuous? Well, because we believe our prior knowledge tells us. We believe that the world is fundamentally smooth. Okay? In this world, many phenomena are fundamentally smooth. There's very few discontinuous events in this world. Underlying many things, we have a continuous and smooth phenomena. That's why we regularize things. Okay? Like putting a constraint on the second order derivative to force it to be smoother, because that's our prior knowledge about how the world operates. If you look at any non-parametric method, okay, all non-parametric method, the underlying prior, because all the non-parametric method is produce an estimate by averaging the values in the neighborhood, right? We know K and N, and for any other non-parametric method we have not introduced before, so far, what is a typical non-parametric method? Like what is K and N? I said it. Suppose we have a bunch of data, okay? So if I want to know EY given x equal to 4, right? Our typical example at the beginning of class. Now this is x equal to 4. Why am I, so there's no data here, there's no y here. So in order to non-parametrically estimate the y, what I do is I include this neighborhood, right? Okay, and I average these points. But why? Why can I do that? Why can I average the neighbors? Well, there's underlying assumption, which is the points, which is the function f. Okay, so there exists the underlying true function. But what if the underlying true function look like this? Okay, suppose the underlying f look like this. Well, maybe even worse, something like this. Okay. Now, if the underlying function f look like this, okay, look like this, discontinuous or semi-continuous, can I average the neighbors to find out the value of f? I cannot, right? Okay, so if in this window it goes like this, the f goes like this. In this window, suddenly there's a sudden drop. Then in that case, if I average the points in this window, I will now be able to get the true f. So under what condition can I get the true f? When f is smooth and continuous, right? If f is smooth and continuous, then I can average. Then if I average points in the neighborhood, that will approximately tell me the value of f in this point I'm interested in. In other words, all non-parametric methods, is based on a prior belief that the underlying f is continuous smooth. At least in every region we're averaging. Okay, so the averaging technique to produce non-parametric estimators is based on the underlying prior belief that the world is smooth and continuous. Right. So regularization is a way to introduce this prior belief into the frequentist estimation so that we can better incorporate that. Right? Okay, so that's one way to think about regularization in what we're doing. Right? And it makes perfect sense in that case why you understand why we want to regulate and why we want to constrain the complexity. Right? Okay. Now, if you still remember the Darren, what's his name? Darren Baum or something? The Cornell guy, psychologist who produced a research paper saying that people can sense the future because, especially when they're watching porn, right, movies, the pictures. The problem with that research exactly is because we haven't, like I said, one reason, right? There can point to several reasons, small sample size, etc. But one of the main reasons is he just did an experiment, and based on his data, he calculated p-value. It's statistically significant, and then he declares we have found a truth. The problem is, again, there's a lack of ability to incorporate prior knowledge. Because, like I said, we have thousands of years of human civilization, which all tell us this is impossible. So based on our prior, we should have a very strong prior that's centered around 0. That essentially extremely small standard deviation for our prior, right? Almost 0 standard deviation. We should say it's impossible to be sensing the future. So if we are able to incorporate our prior in that case, then even if our data, even if the data, like a random experiment for some random reasons that produce some significance p, even if the data tells you that there is some theta, your posterior is still significantly correlated, centered around 0, right? So that's the benefit of incorporating prior knowledge, and you can think about lasso on the ridge as exactly doing that when we say the beta should be centered around 0. Of course, I should be careful because I don't want to push it too far. There are we should not shrinkage method like lasso on the ridge regression should not only be understood as incorporating prior. Okay? Incorporating prior is one reason why we want to do shrinkage. But there's also another reason why we want to do shrinkage. There are two important reasons. So far I only talk about one reason. The other reason is statistical. It has nothing to do with prior knowledge. The statistical reason is very simple, which is we already talked about. I want to bring down the variance of my model. It's just that simple, okay? So sometimes you do shrinkage because you want to bring down your variance. It has nothing to do with your prior belief. Sometimes you do shrinkage because your prior belief tells you that the beta should be sparse. Okay, so that's also related to another point I have talked about before, so let me just sort of state it again. When we are choosing a model, okay, what are the things that should determine whether we should choose a complicated model or simple model? There are two things we should consider when we choose a appropriate model. One thing is how complicated the underlying f, the true f is. Okay, what the world truly look like. So the true complexity of f will tell us how complicated our model, the best model, should be. But the second is how much data we have. If your data is very limited, then you should choose a simple model, even if the underlying f is very complicated. Because when your data is limited and you choose a very, very complicated model, even if you choose the true model, okay, even if you use the true model to fit a very limited set of data points, your fit will be very bad. Its variance will be too high. Okay, so the choice model depends on two things: what the underlying f truly looks like, and how many data sets, how many data points you have. What's the size of a sample? Similarly, when we are choosing regularization, we are also, or whether to do regularization, or what kind of regularizer we use, we are also influenced by these two criteria. The first criteria is, what is my prior belief about the underlying, like what about what the beta looks like, or what about the f look like, right? So I should choose the regularization based on my belief about the underlying, like my prior, okay? But the other thing is I should choose regularization or regularizer based on the sample size. If my sample size is small, then I should regularize because my model cannot get too complicated. Otherwise, the variance is too huge. So that is a pure statistical argument for shrinkage method. So both matters, okay? Both will come into consideration, and both explain why we do lasso or ridge or elastic net in reality. Okay, so that's so much I want to talk about in model selection and regularization.